I would like to take the opportunity to discuss memory management on operating systems, and specifically I'm focusing on the aspects related to paging and the varying connotations relating to how that generally works, and the generally varying techniques that are implemented or algorithms that are utilized in order to ensure that that's at a functional state from a low level to a higher level understanding. And I think that the focus at present would probably be most likely on the Windows operating system implementation of things with a general overview. So the first thing to understand, or to begin to understand, is that memory itself comes in various forms. You have main memory and secondary memory. Main memory being RAM, or physical memory in one aspect or another, and secondary memory being long-term storage, such as a hard disk. Now, in that understanding, the physical memory itself has to be prepared in order to be utilized by the operating system, and this occurs through the process of a method called segmentation. And segmentation basically allows you to separate because if you don't do that, then the address space is completely open and it's just the hardware in itself, and it limits what the operating system can do in regards to the logical capabilities of its general operations. Now, when we consider that, we can begin to look at segmentation as a mechanism to split process or to split physical hardware or physical memory into different logical components that can then be allocated to specific processes, right? So if we have one big block of RAM here, and we have process A, process B, and process C, and then I don't know if that's visible or not. However, what then happens is that the operating system can allocate a particular segment, and can allocate this segment here and then this segment here, or this process here, to be utilized in RAM, and these though are fixed size, so there's an issue to that. Fixed, or you can get some that are dynamic. This is very, nowadays it's mostly dynamic, and this generally doesn't work as pretty much intended, because this is just segmentation. It comes with many limitations and many issues in itself, so that's pretty much that. So A will be here, C will be here, and B will be there. And basically that's pretty much that, and then you can swap these in and out of memory as intended. However, since it's a fixed size, the programs themselves have particular issues in relation to how they can then be allocated onto these fixed size segments, because processes come in different sizes, and you can get sometimes you can get fragmentation that may occur where a process is smaller than the actual intended outcome of the overall system itself. So that can be problematic, and that can be an issue in itself, because resources are then not appropriately utilized in this particular section here. So that can be an issue. And sometimes the process can be too large for a particular scenario or environment, and in such situations what we do is we can have either larger fixed size segments or split the process up in one way or another, which can be a bit detrimental. However, just the point that I'm trying to make here is that this as a mechanism is not really the best mechanism or the only way to have an efficient system. Let's see if I can get some extra light there. So what we have now is that we're going to look at the alternative option, or another method which is utilized alongside segmentation to enable it to be more robust and more successful in relation to how it functions. So this is paging. And paging basically is a similar concept where we have memory, and these bits here have been segmented into whatever blocks of memory that can be required based on the architecture of the system, either 32-bit or 64-bit. And then we then have processes and process A, B, and C. And then what we do now is that we ensure that these processes themselves can be split up into particular sections. And these sections themselves are held together by a process control block. Just I'll put PCB, pretty much easiest thing, PCB, right? So that's the process control block, and then that manages all the memory and all the other things that may be necessary when actually defining how a process should be managed in essence. And then what then allows us to do is it allows us to place these particular sections into memory, or into sections of memory that are completely dynamic and that are completely unique in themselves, and then those are actually swapped out and are requested and are requested as and when needed. So here we can have the blocks here. So the blocks here will represent a section of memory, whether be it however size, it could be 4 KB, which is the usual size. Right, so we can then have in here we can have a page from process A, and then we can have a page from process C. We can have a page from process B, and then C, B, A, C, B, right? And then these pages here are all just like pretty much dynamically allocated as and when needed by the operating system. So we're still making use of segments. We've got dynamically somewhat sized or fixed size dynamic segments. Doesn't make much sense, but because there's so many more of them, it enables you some level of flexibility, which is the paging aspect. So you still have the fixed segments, but you have the paging aspect of it to add that dynamic nature to how that's managed. So the memory management is actually the process of actually managing how these pages are swapped in and out of memory, in essence. And there's a bunch of things that come into play relating to how that actually occurs. And there's a bunch of translation mechanisms that are utilized in order to make sure that the software itself is able to appropriately do this efficiently based on varying algorithms and varying data structures such as the PCB. So we're going to discuss a little bit about how this actually works. Yeah, so that's paging and segmentation, and then now we're just going to discuss how this is actually organized. Mainly, how does one process protect memory from another process, and also how that swapping in and out occurs, and what that basically, what benefits are brought forth by that general functionality. And then we can also look at a bit of virtual memory, which I think is important. However, I think that this memory management aspect thing will be the first thing and the main key thing. So what we have is the following, right? We have we have a page directory table. PDT, and then we have a page, and we have a page table, and then from that we then have a page directory table, we have a page table entry. We also have some over here, a segment table, if I'm correct. And then there's the global descriptor, table. And this in essence is what formulates the overall things that form. So here we're going to have memory. Cool. Memory has been split up into 4 KB chunks of memory. And here we have our process. Cool, right? PCB there, amongst other things. PCB stores is basically the data structure. And this is going to be split into varying pages of 4 kilobytes each if you don't have PAE enabled, which nobody does anymore because everyone's got enough RAM nowadays. So this here is a memory address. Cool. And then what that has the ability to do is it's composed of specific aspects and attributes. And I understand that in here you have a value to a segment. Then you have a value to the PDT. Then you have a value to a page table or to a page table entry. Which then has an offset into the appropriate location in memory. So, you know, you normally have an address written in some hex format here. So say AC13B4. And basically these will be segmented as shown here, and then what then this does is that it does the mechanism of conjoining those segments to actually formulate these lookup capabilities here. So for example, it might look into, so as the machine receives the memory address, it will identify the segment. I'm getting a bit confused here in regards to how these here tend to operate, and also the structure of this memory address, but I think that's fine and that's okay. So basically it'll go into the segment, and then that'll ideally assist it in identifying the actual memory location or memory region and that side of things, depending on what it's actually trying to access. And if, for example, this is local to the process, then this in essence should be fine. However, that segment itself might assist in identifying a region in main memory, and then you have the page table entry, the page directory table, which holds the reference to the appropriate page table. And then in the page table, when we get to the page table, we're then able to look up the value or the particular entry or the memory that we're looking for. And then from that onwards, that should give us some location in main memory, like on our region of main memory, because don't forget that this still has segments, right? And then at this point here, when you get to the page directory table entry, we're trying to identify where our pages that we're looking for in that particular region of memory. And all this is occurring in the process. So now we then go and we find, or at least we get the offset from here after we've identified where our page table is, pretty much. I'm going to have to relook, or this conjoins into that. These two are together, I guess. Yeah, and that's my current understanding of it. And all this here is occurring in the process. And then if you want to access like a memory section that's like not one in the application itself, a global memory, or for example an external library, you then get reference to the global descriptor table, and then that will in essence then direct to the page directory table, to the page table entry, and then give you the location in memory where that will be pretty much located in one aspect or another. So that's my current understanding of things from one perspective or another. It's a bit bizarre, and I don't think that it's completely accurate. However, that's pretty much how general paging pretty much works. Then there's the virtual memory aspect of it, which we'll also get a further look into. So basically now what we need to sort of understand, it looks pretty much in line in essence, though the explanation could be better. We're going to depth and alternative time. So now to understand the aspect of virtual memory, all it does pretty much, which is very key, is that it uses secondary memory, which is the hard disk, to create a swap file. And that file basically enables you to store things that are in main memory to the hard disk, right? And basically what this here is doing is translating the virtual address, because it's an overlay memory, right? Been overlaid. So basically what this here is doing is translating virtual addresses to physical addresses, right? And that's why all this here, the page directory table entry and the page table entry and the segments are all necessary in order to understand how to locate the actual physical location. However, everything in memory is organized differently. When the system starts, it splits the amount of memory between operating system memory, kernel space, and user mode, right? So basically all it has to be managed virtually. So they use virtual addresses, whereas the physical addresses themselves are something else. So we use a translation, or we use this mechanism here to be able to appropriately locate and identify those particular locations in memory, which is important in general. So what we can do now is that to understand virtual memory, we have to understand that, there's a swap file, and then once we have that swap file, basically just a location where instead of things being, it enables us to use more memory on the system, because we're able to effectively and efficiently store pages that are being utilized on disk, instead of ideally terminating the whole process or identifying where those can be located. So to understand that, first thing we need to know that there's a CR3 register, and basically what this register allows us to do is store our page directory table entry address. So each process can have one page directory table, and now what we want to do is we want to be able to swap out from this location here into secondary memory, which is the hard disk, right? Actuator arm and blah 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 blah. Secondary memory. Secondary memory core, right? And then what we have in addition of the translation or translation look aside buffer. So we have a translation look aside buffer, and then what that enables us to do is that it enables us to have somewhere to cache memory. We have somewhere to look up secondary memory. So what this basically does is it enables us to be dynamic with how we utilize the page directory table, because then we can then, instead of directing, okay, I think it's key to explain how pages are utilized in memory. And basically, you know, there's four things that are checked for, which is segment type check, right? So because all these are sort of triggered by interrupts. So if it tries to access a page and the page is not there, then it fetches the page from wherever the page may be located, using these methodologies here, right? So if you can't find the page, it goes looking for the page, and when it fetches the page from wherever the page may be located, be it on disk but not in virtual memory or wherever else in the process that page may be located. So if you can't find that, it either raises an interrupt. It checks for a bunch of different things to ensure that that memory location is valid. However, the key thing to understand is that it raises an interrupt that then fetches that particular page. However, the translation look aside buffer, what that does is it adds a cache, so we can check to see whether we hit or miss. And you can also improve in speed and efficiency, because with having that cache, we can keep frequently used pages locally, and also it just assists in ensuring that, you know, when it's looking for pages either here, when it comes looking to here, this can then do the routing or the direction mechanisms to make sure that it finds the page basically here. And that's what that basically looks like, and that's, I believe it uses these first two bits, but the directory table would have the necessary address that will help us find the location of a particular page or memory section within secondary memory, and then we can swap that in and out as and when required. And this is independent of each process, because each process has a CR3 register, and in the CR3 register, that's where the page table directory entry first byte location is stored, or the first memory address. And then we have the general segments there, but the segment itself is not really that much of an important thing in relation to how this functions. So that's pretty much that. I didn't really do virtual memory that much justice, but that's the general gist of it, and that's the general gist of how memory management sort of works from my understanding of things. I don't have that much practical nature in relation to debugging and actually getting to the internals of how memory itself functions. However, I think that this is a good enough base to be able to explore those concepts to a debugger or whatever else that may be possible when exploring and understanding the varying functions of the kernel.